Welcome back to Physics 142 Online. I'd like to work out a simple example problem involving the Doppler shift equation that we learned in class. It will illustrate basically how to figure out which signs to use for the terms in the numerator and denominator, and it will also illustrate one possible pitfall that sometimes trips people up when they try to make a shortcut and solve problems involving the Doppler effect. So here's the problem statement. You're in a car moving at 35 meters per second, and you're being pursued by a police car with its siren on. So you're in trouble. The police car is moving at 45 meters per second. If the siren frequency is being measured as measured by an observer in the police car is 850 hertz, what frequency do you hear in your car? And we're told to use the speed of sound as 340 meters per second. So we got to start with a sketch, as always in these problems. It really helps to figure out this problem. It's pretty easy to tell who's the source and who's the observer, but that's not always easy in all problems. And so this makes it really clear which is which. The sketch, of course, does not have to be very fancy. We've got you in the moving car being pursued, right, by the police officer with the siren. And so the police officer, the siren is the source of the sound, so we'll put S for source. You are the observer, and you're moving, of course, with a speed of 35 meters per second, being pursued by the police car at 45 meters per second. And we worked out in class at one point the conversion factor between meters per second and miles per hour, and it's a little more than 2. So this observer, you as the observer, are going upwards of 70 miles an hour, probably closer to about 75, and the police car is almost moving at 100 miles an hour. So this is a high-speed chase. So the Doppler effect equation is that f prime is equal to the original frequency f measured with the observer and the source both at rest times this fraction that has to do with not only the speed of sound but the speed of the observer and the speed of the source. And we put the plus and minus signs in here because it could be either one depending on the relative motion. And remember the rule that we get just from our everyday experience with this effect is that motion of either source or observer toward the other causes the frequency to go up, causes frequency to increase. And vice versa. The motion of source or observer away from the other causes the frequency to go down. If we remember this rule, then we can easily assign the plus or the minus sign as is appropriate. Alright, the source, then it says that in the police car, an observer in the police car measures the frequency to be 850, and that's the F that's here because that's a person who's moving in the same frame of reference with the source, and so that's the unshifted frequency. That would be 850 hertz. We're now going to plug in the appropriate terms in numerator and denominator. And of course it's important we see, since I've labeled the source and observer separately, we see that VO is 35, but do we use plus or minus? And the question then is the observer moving away from the source or toward the source? Here the observer is moving away from the source, so the frequency has to be shifted down, which means, right, we've got 340 meters per second, and for the frequency to be shifted down we have to subtract the 35 meters per second. So that's the contribution due to the observer motion. Then for the source motion, 340 meters per second again is the speed of sound. The source, however, is moving toward the observer, and so that effect should cause the frequency to go up, And the only way that happens is if we have a subtraction in the denominator, right? If we use the plus sign, that would make the denominator bigger, which would cause the frequency to go down. But if we subtract 45, that would be consistent with the rule that says the frequency should go up. And so that's all there really is to it in this problem. If we plug those numbers in and report the result, we get 879 hertz, which clearly is greater than the original frequency of 850. And so this means that the net effect has been for the frequency to be shifted upward. That's really about all there is to it for this problem. However, be careful. And this is where I wanted to illustrate a pitfall. And it's a pitfall that really only clever students would fall into, because you might look at this situation and say to yourself, hey, could I solve the problem by simply making the observer, assuming the observer is at rest, and the source pursues the observer with a speed of 10 meters per second, which is the relative speed of the source with respect to the observer. And I'm going to show you that you can't do that. Don't do this, but I'll show you why and what happens. Don't do this, which would be to redraw the picture with, right, the observer at rest, VO equals 0, and with the source moving still toward the observer at 10 meters per second. So if we do that, we'll see right away that we'll get the wrong answer, because we'll end up with 850. And this fraction, if VO is 0, right, then the numerator would simply be 340 meters per second, and the denominator would be 340 minus 10 meters per second. And if you crunch the numbers out on this one, you get 876 hertz, which isn't too different from the correct answer, but it's not correct. It's incorrect. And the reason that this trick, what looks like a simplifying trick, does not work is because both the motion of the observer and the motion of the source can cause a shift in the frequency. And the reason is that the speeds that they travel at are measured with respect to the speed, or with respect to the reference frame in which the air is motionless. So we have an observer somewhere here who's not moving with either the source or the observer. This is someone who is watching them go by, and this is the person who's at rest watching them go by who measures the speeds, right? So if we were to set the observer speed equal to 0 and the source speed equal to 10, we've changed the speeds relative to the observer who actually makes the measurements. And so the simplest way of seeing it is that we've completely gotten rid of the effect of observer motion on the frequency, and as a result this does not work. So no good. Don't do it. It's tempting, but it's wrong. Well, I hope this example helps to illustrate a simple Doppler effect problem. There are some more challenging ones on your homework, and I hope you get to work on those. I'll see you in class.